Hello friends, I'm Dr. Rupali Indait, Assistant Professor, Department of Chemistry, Radhabekani Mahila Mahavidyalaya, Ahmednagar. And we have to see agricultural chemistry, problematic soil and soil testing, that is chapter number 2. And today we are going to see part 2. In that second part, we have to focus on reclamation of alkali soil. The reclamation process depends on the type of alkalinity. And this reclamation of saline soil is done by following methods. Either we can reclaim the soil by removing excess of salts, either by scraping the salts from the surface as well as washing them down into the lower layers beyond the root zone. By growing salt tolerant plants, we can reclaim the soil. We can use two or more these methods at a time. Alkali soil cannot be reclaimed by flooding the land because this soil contains free calcium carbonate. But the addition of substances which produce the acidity we can use for the reclamation process, like FYM, that is farmyard manure, green manure, sulfur, molasses, iron and aluminum sulfate we can use for the reclamation. The acidity developed during the course of their decomposition in the soil neutralizes alkalinity and at the same time brings calcium carbonate into solution, which then reacts with sodium clay and converts it into calcium clay. The carbon dioxide liberated by the decaying organic matter and by the plant roots increases the solubility of calcium carbonate, due to which the concentration of calcium ion in the soil solution is increased. The H2SO4 also increases the concentration of calcium ions by dissolving calcium carbonate. The growing of salt-tolerant crops which can also withstand waterlogging, such as rice. After that, concentration of soluble salt has been sufficiently reduced to allow their growth helps the reclamation process. We can use acidifying fertilizers such as sulfur phosphate and ammonium sulfate increases acidity in soil and maintains fertility. Suitable crop rotation, including salt-tolerant crops, helps to reclaim the process. The crop root also helps to increase the permeability of the subsoil by exerting CO2 pressure and developing cracks in it, which allows easy percolation of water. Then we see the classification of alkali soil. Alkali soil is mainly classified into three types. First one is the saline soil. Second one is the saline alkali soil, and last class is non-saline alkali soil. Now we go through each and every class. See the first one, saline soil. The soil which contain excess of sodium salts, but the clay complex contain exchange of exchangeable calcium is known as saline soils, or it also called Solonchak. The process of accumulation of salts leading to the formation of saline soil is known as salinization. The composition of soil depends on the composition of rock and nature of weathering process. This soil generally contain chlorides, sulfates, nitrates of sodium, calcium and magnesium. Some soils also contain potassium salts. Soluble carbonates are absent in such soils. And the soil is also known as white soil due to presence of sodium chloride and sodium sulfate, which impart white color to soil. Sometimes the color is brown due to presence of calcium chloride and magnesium chloride. The pH of saline soil is in between 7.5 to 8.5. ESP is very low for this soil, and we can calculate the ESP by using the formula, that is ESP is equals to 100 into exchangeable sodium divided by CEC, where ESP is nothing but the exchangeable sodium percentage, while CEC is cation exchange capacity. The clay particles of the soil are well granulated but do not have well developed structure. It has high salt concentration. It is permeable to water and air. And due to presence of high salt content is harmful to the crops. Then we see saline alkali soil. On accumulation of soluble salts in a soil over a prolonged period, sodium is the predominant cation in soil solution, while plant absorb calcium, magnesium and potassium. Sodium is not an essential nutrient except for a few crop plants. Due to the evaporation of moisture of soil or absorption from plants, calcium carbonate and magnesium carbonate or calcium sulfate gets precipitated, thus increasing the sodium concentration. When the concentration is above 50% of the total cations, sodium ions replace the exchangeable calcium and magnesium ions of the clay complex due to high concentration. Though the reaction is reversible, calcium salts are removed in drainage water as soon as they are formed, thus making the reaction unidirectional. The process of converting normal soils into alkali soil is called alkalization, and the soil may contain sodium clay and excess of salts or only sodium clay with no soluble salts. If the soluble salts are not leached out due to insufficient rains, then the soil contains sodium clay and excess of sodium salt in solution. That is known as alkali soil. Its pH is less than 8.5 and ESP is more than 15%. Then we focus on non-saline alkali soil. When soluble salts are removed by leaching as a result of the increase in rainfall or due to the fall of water table or by irrigation water washing them down or for any other reason, it gives rise to non-saline alkali soils. It contains colloidal complex saturated with exchangeable sodium and insoluble salts. The soil changes depend on the presence or absence of free calcium carbonate in it. How the reaction takes place? Sodium clay on treatment with calcium carbonate, they show the cation exchange reaction and we get a calcium clay with the removal of sodium carbonate. Free sodium carbonate reconverts the exchange complex into sodium clay due to low concentration of soluble calcium carbonate. Due to presence of sodium carbonate, soil organic matter makes black solution, which on drying forms black patches on the ground surface with black deposits on soil particles. And this soil is known as black alkali soil. The clay gets deposited in the lower layers, making them impervious, having prismatic or columnar structure. These soils are called solanates. The process of development of these soils from saline soil is known as solonization. The soil reaction is strongly alkaline. The pH having the range 8.5 to 10 and ESP is greater than 15%. Drainage and aeration are poor, because of which swelling of the clay takes place. Due to this, soil pores are chokes. As a result, the soil loses the crumb structure. The presence of free sodium carbonate has a positive effect on plant root. Due to the high pH, the impaired physical condition of the soil, and toxic effect of free sodium carbonate and exchangeable sodium adversely affect on plant growth. These soils are therefore almost barren soil. Then we see the next type of soil, that is degraded alkali soil. The changes during soil development is slightly different when it does not contain free calcium carbonate, which results in the prolonged leaching. The sodium clay hydrolyzes and liberates free sodium hydroxide, which combines with the CO2 of the soil air and forms sodium carbonate. See the reaction: sodium clay on treatment with water molecule, it gives hydrogen clay plus sodium hydroxide. Again, the sodium hydroxide on treatment with the carbon dioxide, it converted into sodium carbonate plus water molecule. The humus gets dissolved in sodium carbonate and the solution passes down to the lower layers, which acquire black color due to its deposition. A part of exchangeable sodium is also replaced by H+, which breaks into silicic acid, which is also leached down along with humus. This process is known as solidization, and the soil so formed is called solid or soluth or degraded alkali soil. It is acidic in nature. The pH is 6 while ESP is greater than 15. It is very compact and has low permeability. Then we focus on tolerance by plants. Both saline and alkali soils are harmful to plants on account of the excessive concentration of soluble salts in soil solution. Large amount of salt in solution increases the osmotic pressure and reduces the uptake of water, which causes plasmolysis. Plasmolysis increases with the concentration of solution until all the functions of plant collapses completely and the plant finally dies. In addition to the total salt concentration, the harmful effect of the salt depends also on the nature of salt present, the plant species, the nature of the soil, especially its texture, and the distribution of salts in the profile. Sodium carbonate is the most harmful salt as compared to sodium chloride and sodium sulfate. In alkali soils, the exchangeable sodium in the colloidal complex reduces the availability of calcium and thus prevents its intake by the plants. Growing plants under such conditions are die due to lack of sufficient water. Salt tolerance varies also with the age of plants. Plants that have deep root systems are able to tolerate salinity better than others. Growing plants in sandy soils are able to tolerate a greater concentration of soluble salt than those in clayey or other fine textured soils. Climate also influences salt tolerance by crops. Growing plants in arid and semi-arid regions are able to tolerate greater salt concentration than those in semi-humid and tropical regions. Here we see how the plant can tolerate it. Thank you.